Hi everyone, my name is Jackie, a PhD student from the University of Maryland. Today I'm excited to share with you our work in IRP and exact combinatorial optimization framework. We have integrated the RL-based initialization, and our primary application area has been the scheduling problem. Let's dive into more details about it. Here is today's agenda. We will start with an overview of the combinatorial optimization and the DN scheduling problem. Then we will discuss the motivation behind our research and introduce the current approaches. Next, we will transition into our work in IRP and have a close look into the design details. Finally, we will talk about the evaluation part. Under the predefined scheduling constraint, DN model scheduling is about to find the best pipeline scheduling solution for a DAG-based DN graph in terms of the scheduling objective. It can be on-cache memory usage or communication cost between different stages. Let's use a toy example in this page to illustrate it, where the only difference between the two schedules is the convolution tool. From the memory usage perspective, the left schedule outperforms because it has the balanced memory usage for each stage and smaller communication cost. It brings the improvements of the runtime and the energy efficiency. We are dealing with a huge search space for scheduling problem. I'd like to show you some runtime results from over 900 different scheduling solutions for model ResNet 152 in 4-stage pipeline edge TPU system. You can see the results in the figure of the left side. DN model scheduling is a classic combinatorial optimization problem, and our analysis gave us a few key insights. First, off-chip DRAM usage dominates the scheduling quality. In fact, inefficient scheduling solution can result in 2 times of the performance degradation. In this page, we highlight several DN scheduling approaches. On the one side, we have some popular heuristic algorithms, like the list scheduling and the force-directed algorithm. While they can address a problem within several seconds, they don't offer the determinism and can't guarantee the optimal scheduling solution. In the contrary, exact method can provide the optimal results, but they suffer from the scalability issue. As the problem complexity grows, navigating through the expanding and increasingly complex search space becoming more difficult. Finally, learning-based approaches has been utilized for combinatorial optimization problem solving like the scheduling. This method aims to provide the near-optimal solution with inference runtime overhead to improve the scalability. However, they also lack the determinism and can't guarantee the optimal performance. Given what we have discussed, it prompts us to wonder, can we find that ideal scheduling method, one that can seamlessly combine the optimality, scalability, and the determinism? Our answer is initialization. As we all know, navigating the entire search space of the combinatorial optimization problem using exact method is difficult. But what if we utilize the initialization to prune the search space? By doing so, navigating the narrowed search space after initialization will be much easier. Our framework is Iccad. It employs a reinforcement learning-based scheduler for coarse-grained initialization. We introduce a method to relax the search space, then use the exact method to pinpoint the optimal solution. Our framework provides both of the optimality, scalability, and determinism. This is the overview of the Iccad. It takes the DN graphs as inputs and generates a scheduling solution. The problem-solving process includes 3 important phases: initialization, search space relaxation, and exact solving. First step is initialization. Initialization can significantly reduce the search space. By starting with a plausible solution, the optimization process can be quicker and may cover the desired solution more efficiently. A good initialization can help the algorithm avoid getting stuck in the suboptimal solution, thereby increasing the chance of finding a global optimum. Phase 2 is search space relaxation. Space relaxation simplifies the optimization problem by loosening constraints. making the complex problem more tractable. After relaxation, we get a new third space which should contain the global optimum solution. The last step is exact solving. While the exact solving for a combinatorial optimization problem is an NP-hard problem, the refined third space on the top of the initialization is significantly simplified due to drastic third space reduction. Now let's have a close look for the design details of Iccad for each phase. First, we have RL-based coarse-grained scheduler. In the RL scheduler, graph embedding consists of two important attributes, graph structure attributes and the operator attributes. Graph structure attributes consist of the topological order of every node and the parent topological order. Operator attributes record the information of every node, like the memory consumption. In a word, graph embedding aims to transform the node attributes and the data dependence into vectorized representation, which is key information to build the RL model. The RL agent has an encoder-decoder based structure. Both of the encoder and the decoder has 128 LSTM cells. Encoder processes a queue of nodes inputs and converts them into a context sequence. The LSTM decoder generates the selection probability over all candidate competition nodes. Besides, we also integrate the point network as our attention mechanism. For RL formulation, we utilize the exact approach to generate the ground truth label for RL agent training. For a reward function, we use the cosine similarity to minimize the difference between the output of the RL scheduler and the ground truth label. A significant challenge for RL model training is the latent training datasets. To address this, we utilize the synthetic dataset for our RL training. In this approach, we randomly generate the node attributes and compute the ground truth label using exact method. To balance the data coverage and the graph size to minimize the training efforts, our training computation graph are consistently sized with 30 verticals with different graph complexity from 2 to 6. It allowing us to control the complexity without needing vast data collection. The second phase is the third space relaxation. Here we use this toy example to illustrate this process. First, the RL scheduler pipelines the input model into two stages, and we utilize the as soon as possible approach to generate the topological order. The topological order of this toy example is shown in this figure, where the green nodes are assigned to the stage 0 and the pink nodes are assigned to the stage 1. Next, we identified what we called the boundary nodes. These are nodes where either of the parents or children nodes fall into different stages. Now, assuming the relaxation level set to 1, any nodes that have just distance 1 away from of the boundary nodes will be rescheduled. All of the rescheduled nodes will be fed into ILP solver for refinement. The last phase is the exact solving. We use the integral linear programming for refinement. It contains several constraints like the data dependence constraint, parameter caching constraint, and the communication constraint. Besides, we also introduce some auxiliary constraints to represent the Boolean representation. For objective, it contains the peak of cache memory, total of cache memory among all of the stages, and the communication cost. The different objectives are solved incrementally, which means each of the subsequent objectives narrow down the solution space based on the previous objective. The data dependence constraints are formulated as follows. For each edge Eij that directs from node I to node j, dependence formulation is required to make sure node j can be executed only if the node I is completed. So Si minus Sj should be less or equal to 0 if we use Si and the Sj to represent the stage of node Ij. For parameter caching constraint, it requires the memory footprint of each stage should be less or equal to the peak memory usage M limit. The peak memory usage M limit will be one of the objectives for later optimization. Here we have a simple example to illustrate it. Except the data dependence and the parameter caching constraint, we also have some constraints to address the communication cost and express the Boolean equation. For more details, please refer to our paper. This slide is the system integration. In our system, the first step involves the DAG generator, which extracts the DNA model structure to form a DAG. This includes important details such as the operation nodes, edges, and tensors. Following this, IncLP uses the derived graph to inference and generate the scheduling solutions. We employ the Google's toggle converter to split and quantize the models, turn it into TensorFlow TF-led model that is ready for deployment. Using the Edge TPU compiler, these TF-led models are prepared for deployment on the Edge TPU platform. Importantly, we have taken the in-data quantization into account at the IncLP design step. The multi-stage pipeline Edge TPU system is shown in this figure. In order to evaluate IncLP's performance, we use 10 models as a benchmark that is shown in the left table. We have compared IncLP's performance again with the exact method and the heuristic-based Edge TPU compiler. For the exact method, we utilize the IBM Simplex integer linear programming solver. For the real-world test platform, we have set up an Edge TPU systems with options of 4, 5, and 6-stage pipelining that is shown in the previous slides. Alright, let's move into our evaluation results. Gap to optimal analysis. Here we examine the difference in peak memory usage between the IncLP and the global optimum. Here we have several takeaways. First, our IR-based pre-scheduling set a solid foundation for subsequent exact IRP solving. To illustrate it, 3 of our benchmarks hit the global optimum without any exact refinement in all pipelining options. Take the model ResNet 50 for instance. It achieves the optimal results with a relaxation level of 0, meaning our IRP scheduling pinpoints the global optimal solution. The quality of results of the initialization indicates us we can find the global optimum without extensive space relaxation. Second, most benchmarks achieve global optimal scheduling results with small relaxation level. We observe that for all graph tested, the 10-level relaxation is sufficient to generate global optimal results for all cases. Increasing the relaxation level beyond 10 brings marginal benefit but could reduce the advantage of IncLP in solving runtime speedups. Even the size of our computation graph benchmarks ranging from 134 to 782, the relaxation level to secure optimal peak memory results remained consistent. This demonstrates IncLP's robust scalability across diverse benchmarks. Another part of the evaluation is the solving runtime. IncLP provides significantly solving runtime speed up. Considering the relaxation level is 10, it guarantees global optimality. IncLP provides 54, 128, and 115 times speed up for 4, 5, and 6-stage scheduling options over the exact method. Compared with the heuristic-based Edge TPU compiler, IncLP provides 27, 22, and 19 times speed up for all pipelining options. The last part of the evaluation is the onboard runtime performance. IncLP has the optimal quality of results and provides the identical scheduling results with the exact method, which brings the huge runtime performance improvement. For example, IncLP provides over 4 times of the runtime speedup for model ResNet 152 in 6-stage pipelining options. Thank you for your attention. I'm looking forward to answering any questions.